So we really didn't even get really into electrochemistry last time, but we were going over balancing redox reactions, getting familiar with that again. The one that we didn't do was this last one in basic conditions. So go through this one real quick. And for last week's video, the audio cut out after like 5 minutes. So I either need to re-record that, or you could honestly probably watch the my Chem 20 lecture on redox reactions. It's chapter 16 in their playlist. It'll go into even more depth than we did for this. So, and at a slower pace because it's Chem 20. All right, so balancing redox reaction in basic solution. The steps are the same, but at the very end, you neutralize all of the acid, or H+, by adding OH- to both sides of your balanced chemical reaction. To start then, we need to identify the two half reactions. So one half reaction is going to be, even though I can use red now, I'm not going to, the ClO- to Cl, and then the chromium complex to chromate. And so the one half reaction will be ClO- to Cl-, and then the other half reaction will be CrOH4- to CrO4 2-. First step for any of these reactions is going to be balancing everything that's not hydrogen or oxygen. So in both cases, we're good. One chlorine on either side, one chromium on either side. Then you balance oxygen. Balance oxygen by adding waters. So for every oxygen that you need to add, you add one more water to the other side. So for the chlorine, or hypochlorite to chloride, we'll add one water to the right side. For the chromium half reaction, we actually don't need to add any oxygens, because that 4OH is already balancing with the chromate. So then we can add hydrogens now as H+. We need 2 of those in the top reaction. And we're going to need 4 the bottom reaction. Let me know if you have questions or if I need to slow down. I'm on my second rock star today. And then we balance the charges. And I think the trickiest thing about balancing charges is that you're adding negative charges, because we're adding now the electrons to balance these charges. So every electron you add makes it more negative. So you can only add electrons to the side that's more positive. So for a top reaction, on the right side, this is 1- and this is 0 charge. So that side's 1-. The other side, though, has 2+ and 1-. So it's going to need 1 electron on that side. For the second reaction, we're going to add electrons to the right side because we added electrons to the left side already for the top reaction, right? Adding the electrons here is showing, really it's tabulating the electrons that are being exchanged as a part of the redox reaction. No! New projector, why? No. You're supposed to bring balance to the force. What happened? It says I'm still connected, but it's... Okay. What? It says no signal. Okay. How? What if I do this, and then do this? Okay. Whatever. All right. Electrons. We're doing electrons, balancing charges by adding electrons. So looking at our bottom reaction, this is 1 minus charge for the reactants of the chromium half reaction, 2 minus, and then a 4 plus. So then this right side overall charge of 4 minus 2 is a positive 2. And we need to get that to -1 to balance the left side. So we need to add 3 electrons. What's the next step? Oh. Yeah, multiply the top first. And then, yeah, I think the way the book says to do it, so we're going to multiply the top because we want both half reactions to have the same number of electrons. So multiply the top by 3. And so that'll give us, I'm going to take advantage of the fact I can use red. 3, 6, 3, 3, 3. And the way the book says to do these is to add hydroxides at this stage. But I think it's easier to add these together first, then balance or neutralize all of the H pluses with hydroxides. Because then we only have to rewrite the whole equation once instead of writing both the half reactions and then rewriting the whole equation. So adding to these together, we cancel out the things that are the same on either side of the half reactions. So our number of electrons is the same. So those will, whoops, I want to erase it. Cancel out. We also have 6 hydrogens on one side, 4 on the other. So these 4 will cancel out completely, but that'll leave us with 2 still on this side. And then everything else should remain. So we'll get 2H plus 3ClO minus plus CrOH4 minus. And then we do CrO4 2 minus plus 3Cl minus plus 3H2O. Okay. Now we add hydroxides. So we have to add them to both sides of the reaction. And we'll add as many hydroxides as we need to neutralize out the hydrogens. So in this case, that's going to be 2OH minus to both sides. So 2 over there plus 2 over here. And then those 2 hydroxides being neutralized, or neutralizing the 2 hydrogens, is going to create 2 waters. And that will cancel out some of the waters between both sides of the reactions. So we'll lose 2 of these. And so there will be 1 water remaining for that side. So this will be 2 H2O plus 3 ClO minus plus CrOH4 minus 2 minus 3Cl minus plus 1 H2O, don't need to write the 1, plus 2OH minus. Those are always a lot. Back in business. All right, now we can move on to the other stuff, the rest of electrochemistry. Redox is just part of it, and actually most of it that we're going to talk about is about electrical current, how to predict which way, and this is really important actually, which way the electrical current is going to flow. So electrical current is the flow of electric charge. So we're going to be talking about it as electrons through a wire. And by using redox reactions, we can generate electrical current, right? Because we're in a redox reaction, there's electrons being lost by one species, electrons being gained by the other species. And so if we can separate those and connect them with a wire, we can force the electrons to take a roundabout path and use that to do work. That's how batteries work. But whether or not that circuit is going to produce electrical current in the direction that we want depends on the oxidation potentials of each of the species. So zinc, for example, has a greater tendency to lose electrons. And so when we set up this redox reaction, zinc loses 2 and copper gains 2. And then as that zinc metal loses its ions, it dissolves into the solution. And as the copper ion starts picking up electrons, it will deposit itself onto the electrode. This is written weird. All right, so in here we have solid zinc, and it's giving electrons to the copper. And then on the other side, we have copper atoms attaching here and releasing zinc 2 plus ions. We'll look at some different diagrams. I'm probably going to raise the projector. So, like I was saying, if we can separate the zinc atoms and the copper ions from each other, then we can make the electrons take a different path, generate that electrical current. So an electrochemical cell is what we're going to be working with, and they're a device in which a chemical reaction either produces or is carried out by an electrical current. And the first half of this chapter is all about spontaneously generating electrical currents, and that's a voltaic cell. Later, we'll talk about electrolytic cells, where we force electricity to flow in a way to cause non-spontaneous reactions to happen. But for now, we're going to focus on the voltaic cells. So here we've got zinc and copper again, but now we've separated them into 2 separate solutions. And so on the zinc anode, zinc ions are losing electrons that travel through the wire, turn this light bulb on, and into the cathode, where they're deposited into copper atoms, which then become ions in the solution. So on the zinc side, we're going from zinc 2 plus to zinc metal. On the other side, we're going from copper metal to copper 2 plus. So an oxidation reaction and a reduction reaction. And the strips of metal where these reactions are actually happening are called electrodes. So each cell is going to have both species of its half reaction. So zinc has a greater tendency to ionize, so its equilibrium lies further to the right, so producing zinc ions and electrons. And then the copper is more to the left, and so it's going to pick up those electrons to form copper solid. I might have said that backwards initially. No, I think I had that right. So the half cells, if the half cells are connected by a wire, then the electrons can flow spontaneously in this case, from left to right, from the zinc to the copper. And then the zinc 2 plus equilibrium shifts to the right, oxidation occurs. And for the copper, reduction is occurring. So these voltaic cells, these ones kind of won't come up more until later, but the electrical current is analogous to flowing water. And so we have, of course, specific terms for describing the flow of electricity. An ampere, or an amp, as it's often abbreviated, is the amount of electrical current per second. So it's the actual flow of electrons. So more amps means there's more electrons flowing. We also have coulombs. So a coulomb is a unit of electrical charge. So 1 coulomb, or 1 amp is equal to a coulomb per second. So it's 6 times 10 to the 18 electrons per second. And then the analogy, so this is like saying a river that's carrying more water. It might be like the Mississippi River, moves very slowly, but carries a huge amount of water. So not a ton of force, but a lot of current. The voltage then, the amount of force that's actually pushing that water, or pushing the electrons, we talk about as a potential difference. And it really is a difference in the potential energies of the initial and the final states. So this is like, I guess the highest voltage would be like a waterfall. So the water flowing from the top of the waterfall down to the bottom of the waterfall has a lot of force behind it. All right, it's a huge change in the potential energy of the water. And so volts are the analogous property for electrons or electrical current. So large potential difference corresponds to a large difference in the change between 2 electrodes and a strong tendency for electron flow, like a steeply descending stream bed or waterfall, versus just moving a lot of water. So electromotive force, which just kind of being mentioned here, is another term for the potential difference. So throughout all of this, we're going to be using cell potentials to determine the flow of electrons in these electrical cells, electrochemical cells. And the larger the difference, the more spontaneous that's going to be in one direction or the other. So the magnitude of the voltage only tells you, well, how much force there is, but the sign is what tells you if it's going to be spontaneous in the forward direction or if it's going to be spontaneous in the reverse direction. And that'll depend on the different reactants, different half cells that we use. So just like with delta G, right, for Gibbs free energy, we had like standard states for Gibbs free energy. We have standard states for cell potentials, and those are going to be the same. So 1 molar for solutions, 1 atmosphere for gases. So which statement best captures the difference between volts and amps? The volt is a unit that quantifies the difference in electrical potential energy, and the amp quantifies the flow, or is it the amp that's the difference in potential energy and the volt that's the flow, or are they really just the same unit? Different units for the same thing. A. Volts is all about the amount of power behind it. It's the amps. We're talking about like if an electrical circuit is dangerous, it's the amps that will kill you, not the volts. The amount of current that gets pushed through your body is what does it. So for the previous cell that we discussed, it was zinc and copper. And so if we have zinc metal plus copper ions, and then copper ions plus, or zinc ions plus copper metal, that standard cell potential is a positive 1.1 volts. So that's a spontaneous reaction. If we replace zinc with nickel, then our cell potential is lower because the difference in energy, the difference in the potential energy of nickel compared to zinc is, or well, I guess I should say, zinc compared to copper and nickel compared to copper, it's a smaller difference in energy. So this is the difference between nickel and copper in terms of potential energy. And for E cell potentials, positive means that we're flowing in the forward direction. So it'll be spontaneous in the forward direction. If we have a negative cell potential, it indicates that the forward reaction is not spontaneous, but also that the reverse reaction would be spontaneous. So the sign is telling us the flow. Just like Gibbs free energy is really telling us which way is going to be spontaneous for any given reaction. Right? Going from a high potential to a low potential for Gibbs free energy, it's the same sort of concept here, but we talk about it in terms of positive volts. So in a voltaic cell, which direction do electrons flow? High potential, low potential, always from the cathode to the anode? Or do they flow from the cathode to the anode? Or do they flow from lower potential to higher potential? A. Always high to low. So that'll tell you the direction of the spontaneous flow. Kind of like if you had different levels of water in a beaker, and if they were connected by a tube. Okay, so this is one of the slides that I changed. There are a lot of different sort of mnemonics to remember these things, like these ones. That oxidation occurs at the anode, both start with vowels. And then reduction occurs at the cathode, so red cat. Reduction, cathode. Whatever works. The better way to remember these is based on where oxidation and reduction is happening, because that does not change. When we move on eventually to talk about electrolytic cells instead of voltaic cells, the signs for the cathode and the anode switch, because we're forcing electrons there to go in the opposite direction that they want. The thing that does not change is where oxidation and reduction occur. Always at the cathode. Reduction is always at the cathode, oxidation is always at the anode. Well, I guess this last one still works. I put it in this category because electrons are repelled by the negative anode. So the idea of the negative repelling and the positive attracting is only true when it's spontaneous. All right, so voltaic cells, electrons only flowing from anode to cathode. Oh, right. So in our sort of diagram of the cell here, or the electrochemical cell, we've added this thing called a salt bridge. That's because if you didn't have that, right, as zinc ions are being produced on the anode side for this reaction, and as the copper ions are being, zinc atoms are being oxidized and the copper ions are being reduced, you would also build up a difference in charge between the either electrons that are coming in or the electrons that are going out and the solution. And eventually you would build up so much charge that the reaction would stop and would not proceed any further. And so to overcome that limitation, we had something called a salt bridge between the two. So it allows counter ions to flow between the two solutions, because we don't want the copper ions and the zinc ions to be mixing, because then the redox reactions will occur directly on the electrodes, and it won't be forcing the electrons to go through the wire. So there's usually a filter plug on the end of these, spongy sort of material, so that you can have this solution going up and over. And the negative ions will flow towards the positive charge at the anode. The positive ions will flow to neutralize the negative charge that's being produced at the cathode. Because as these zinc atoms are losing those electrons, they become positive ions in the solution. And then on the other side, the copper ions in the solution pick up electrons, and we are removing positive charges from the solution there. So you get a charge imbalance. So this is a lot to write out if every single electrochemical cell had to be described by an entire picture. So electrochemical cell notation, either called a cell diagram or a line notation, shortens this down immensely. And it is written to be logical. So on the left side, we have first our electrode, in this case the zinc metal electrode. And then we separate different phases in each half cell with a vertical line. So this is a solid metal electrode, and then we have aqueous ions that are also in the solution. And it also represents the half reaction that's happening on that side. So we have, oh good, these ones are written already. So this reaction up here at the top of the screen, right? It's zinc solid becoming zinc ions in solution. So it reads left to right the same way that the reaction is actually happening in the electrochemical cell. And then the double vertical lines represents the salt bridge. I like to think of it as the two vertical legs of the salt bridge going into the solutions. And then the copper 2+, because on the right side we have reduction happening, so copper 2+ gains electrons, and then it gets added to the electrode, solid copper electrode. So they're written left to right as sort of abbreviated half reactions. If you have reactants and products that are in the same phase, you just use commas to separate them. And then if all of the principal species in a half reaction are aqueous, you have to add an inert electrode, because there has to be something to attach the wire to carry the electrons from the other half reaction. So platinum is an easy one. Carbon is also used as electrodes, or used for electrodes. So as an example, first thing you have to do, of course, is identify what's being oxidized and what's being reduced. So first, what's being oxidized? Remember, oxidation is loss of electrons. Yeah, it's the iron. So iron is going from iron with 0 charge or 0 oxidation state over to iron 2+. So it's being oxidized. So that'll make up our iron half, or our oxidation half reaction. And then manganese then, because actually manganese, no, the hydrogen's not being oxidized or reduced. So the manganese is being reduced. Because here it would have to be manganese 7+. And on this side, it's just manganese 2+. So reduction is gain. It's gaining electrons. So then the oxidation half reaction would include all the species involving iron. So iron solid goes to iron 2 plus, be aqueous. Oh, plus 2 electrons. And then for the reduction half reaction, we have permanganate, the MnO4 minus. And that is being, we'll do it like this, put this here. All right, so that's being reduced into Mn manganese 2 plus. And because the manganese is the only species of our two half reactions that has oxygen, then the water and the hydrogens are also going to be part of its half reaction. So that's how you know where to include those. Because iron 2 plus doesn't have any oxygens, so it's not going to have any hydrogens. So Mn, or the permanganate plus, oh, I should be taking these down with it too. 16H plus, this should be a 2, that should be 5, and that's 10. If we wanted to keep these half reactions balanced, plus 8H2O. So that's why then, when we look at the line notation, right, we have this reaction is the Fe to Fe2 plus, iron to iron 2 plus, and then it's permanganate plus some of that acid, H plus, and then the permanganate being oxidized into manganese 2 plus. And because all of those species there are aqueous, we include platinum or some other inert electrode after the line on the far side. So here's a picture of that reaction written out. Iron anode with iron 2 plus solution, potassium nitrate salt bridge, then all three of the reduction species on the cathode side with a platinum electrode for the cathode. All right. So I don't know why the slides didn't have this in there before, but the question that we ultimately want to answer, just like with Gibbs free energy and thermodynamics, because really electrochemistry is an extension of thermodynamics, is how do we determine if an electrochemical cell will be spontaneous in the forward or the reverse direction? So as I mentioned before, it's all about figuring out the potential energies of each of the species, each of the half cells, and then using those to determine spontaneity in either direction. So for each of our half cells, we can think of each half cell having its own potential, and we call those standard electrode potentials. And so E cell, for the whole cell, two half reactions put together, it's the difference between the two standard electrode potentials. The trick, though, that's the next slide that I added. So we're thinking of this, again, like two beakers with water in them connected by a pipe. And if our anode has a higher water level than the cathode, then the water will flow, or the electrons will flow from the anode to the cathode. So moving from that greater potential energy to the electrode with a more positive charge or the less potential energy. The problem is, though, if we want to determine what the half cells are going to be, we can't just compare a half cell to nothing, because there's no way to determine that standard potential if there's not somewhere that it's flowing to. There's no absolute scale here like we could use for entropy. So what we do instead, and what chemists have agreed to, I guess physicists also, is we'll set something and say that this is the standard potential. And the standard that we're going to be using, the standard electrode half cell is going to be the standard hydrogen electrode, although in the past, different things have been used. I know there's a calomel electrode, which used a mercury electrode. Obviously, don't want to be using mercury, so hydrogen is a lot safer. So this is the reference for everything else. We would say this is 0, and then hook this half cell up to different metals, other metal half cells, and see which way the electrons flow to determine if they have higher potential energy or lower potential energy than the standard hydrogen electrode. And then the way that these are set up is that the standard hydrogen electrode is always the cathode. And so we're always determining if the metal is able to reduce hydrogen or not. But when we tabulate them, they're all reduction potentials. So this chart that I gave you, these are all reduction half cells, or half reactions. So the general setup is that the hydrogen is always the cathode. And then we figure out what the cell potential is, and then calculate the anode potential from the whole cell, just setting cathode as 0. So for, again, going back to zinc, and then we'll do copper again, we would set up this standard hydrogen electrode and measure the cell potential. So the cell potential for zinc as the anode and hydrogen as the cathode will give us a positive 0.76 volts. And then we plug those numbers into the equation for standard potential of the cell, where 0.76 volts is the whole cell. We have decided that hydrogen is 0, and so the negative of that has to be the charge, or has to be the voltage of the anode, and that's its oxidation potential. So here, because it's more negative, because zinc is more negative than hydrogen, I don't like the way that the book does this and talks about it, but the way they say to think about it, which works for voltaic cells but not electrolytic cells, is that the negative electrode potential means greater potential energy of an electron at that electrode. So it's saying that the negative charge repels the electrons towards the positive cathode, which works. And if that makes a ton of sense to you, you can think about it like that. I'm going to show you that it's actually easier than that. If we then look at the copper side of this, again, it's copper as the anode, hydrogen as the cathode. And now when we set this up, the voltage that we measure is negative 0.34. So again, you set up E cell